With this gadget you can actually measure speed and acceleration. Today we are designing the casing for 3D printing and we will test it. There are a number of suggestions on how to measure the speed of a vehicle. Utilizing the signals from two sensors, the speed is calculated from the distance between the sensors divided by the measured time. No doubt about it, this is a resilient method. But we want more at Electronics Unmasked. We want to measure the acceleration too. We are using 3 infrared sensors instead of 2, and we derived the math equations for that. There is an earlier video on Electronics Unmasked explaining the math, the electronics and how to query the sensors using a fast interrupt routine in the code. Definitely a must-see in case you are interested in this topic. Our first measurement results with a cardboard prototype were encouraging, even when its structure was a bit wobbly. That's why we decided to build the Speedo with a solid case. Before we continue, there is a hint to PCBWay, the sponsor of this video. There are once again great offers for PCBs and much more. Just check out the website. And then I'm eager to give you that hint. Discover PCBWay's project database. A great thing to join, because there's a number of really interesting projects. Hey, this is creating a lot of enthusiasm and innovation power. Think about the easy way with PCBWay. Our requirements for the casing are mainly motivated to improve the measurement accuracy. The housing must be mechanically stable and the defined sensor distances must be precise. If possible, the distances should be slightly larger than with our cardboard box prototype. We are designing slit apertures for the sensors to make their measuring cones narrow. All these measures give us more precise trigger points for the sensors, improving the measurement accuracy. We may need to adjust the sensitivity of the infrared sensors on the racetrack, which is why the housing should be easy to open and close. I really enjoy working with FreeCAD and I'm trying to get better with each new project. The upper part of the housing is carrying the complete electronics. The 3 infrared sensors are attached here, and below we see the holes for the sensor LEDs. And then we have a base for attaching the ESP32 board and a bar where we can tie cables. Here comes a little trick. I'm using cuboids to represent the outer dimensions of my electronic boards. This is really helpful when designing the casing. We use magnets that we are gluing here to hold the casing together. This method is proven already with the housing of our slot car lap counter. We can conveniently open and close the casing later. These are the magnets in reality. You can buy them for little money. Of course, the magnets have a counterpart on the other part of the housing. I'm using the following trick so that the parts fit together exactly. You first glue the magnets on one side of the casing and let the glue harden. Then stick a thin piece of tape on the part to prevent the other housing from the glue. Next, you put the magnets on top of each other. Then take the other housing part, put some glue in the recesses provided, and press the 2 housing parts firmly together. Once the glue has hardened, you can open the case and remove the tape. Maybe I exaggerated a bit using 8 LEDs, and we might not need all of them. However, I want to use the LEDs for visual feedback to the racing pilots, because there will be a number of features that we don't want to reveal yet. I'm trying something new with the text extrusions. Actually, a nice way to label the housing. Let's see what this looks like in reality. What do you think about that? Write me in the comments. Then we take a quick look at the lower part of the casing. Of course, I'm excited to see how my extruded logo will look in reality. Inside we can see two recesses where the magnets will go in. Okay, now I need to show you the apertures for the sensors, where I put in some brain power. The infrared diodes are inserted into the round holes, which are merging into cone holes. The cone holes merge into a slit, limiting the incidence of infrared light horizontally. With the long slit, we don't have vertical restrictions for the infrared sensors. As mentioned before, this is giving us a definite trigger point for the sensors. I'm demonstrating the magnetic closure now. It really works well, doesn't it? What do you think about this method? Tell me in the comments. Now comes the answer to the burning question. Is the 3D printed casing bringing an improved measurement accuracy? By the way, you're currently seeing the power on process and connecting the Speedo to a PC via Bluetooth. Although we could not verify the speed measurement accuracy yet, we're convinced that it is fairly accurate. However, we are not so sure about the acceleration measurement, because this is where all three sensors' inaccuracies are adding up. But look at this. We repeat the gravitational acceleration test that we already carried out with our cardboard prototype. The results for the acceleration are reproducible. They deviate only 3% maximum. The result in absolute values also seems very plausible to me, because we are measuring 93 to 96% of the gravity acceleration. You noticed that I'm revealing one of the measurement reports in advance that you can receive via Bluetooth and record on a PC. Our method is actually suitable for measuring speed and acceleration. Speeding cameras are allowing 3% deviation. We can probably achieve this accuracy too, and I think this will be an interesting gadget for our racetrack. Next, we need to talk about the code, and then we go to the racetrack for testing. I'm really looking forward to measure the acceleration and speed of our tuned model racing cars for the first time. Now stay tuned and don't forget to support the channel. See you soon in the coming episodes.